Hello, this is Lim Yi-hen, and this is my project, Low-cost cooking stove with low-cost sustainable fuel using natural or synthetic materials. My supervisor is Mr. Daniel Lim. The aim of the project is to design and develop a stove and find a method to provide better air circulation and also include simulation and analytical calculation. The objectives of the project is to design and develop a low-cost cooking stove by choosing a correct material and also a correct design. This can reduce risk of human health during cooking due to smoke inhalation. The scope of the project is, like I mentioned just now, design a low-cost cooking stove by using SolidWorks and to simulate heat flow in combustion chamber by using ANSYS. The problem statement of the project is 42% of world, about 500 million people rely on burning on biomass material. They use biomass material to burn, such as to cook, to heat up their house. And Lancet study shows 3.5 million people die from indoor air pollution. This is caused by the incomplete combustion and all the toxic fume produced during the combustion. So for market research, the mud stove is the current stove can be found in third world country. It's a stove produced by a mud, clay, and they use a wood, charcoal, or even animal waste to burn. Okay, next is a Michai rice husk stoves. This can be found in Thailand, also India. Okay, this is a stove containing of 4 structural metal pieces: cone, stove body, stands, and also ash receiver. Okay, they use scrap material to make this stove as a very simple and cheap material. The other one is Soksan economy stove, also can be found in Thailand. They made up of bricks, cement, and mixture of clay and also rice husk. They can use any kind of fuel, like I mentioned just now, the waste material, the charcoal, the wood. Okay, next is a later version, and this is the version of the stove that we study and research and use for our further design. Okay, this is also made from scrap metals. It's a form of cylinder, and the door is to be used as an airflow controller to give a better combustion or even a slower combustion. This is the ready product by EcoZoom. Okay, so let's talk about the factor affecting performance. Okay, there's a convective heat loss, conductive heat loss, radiative heat loss, and also size of fuel, type of biomass, air supply, and stove material. We're going to talk about this more detailed. Okay, so about convective heat loss is a gas moving up due to a difference in temperature. Okay, how to prevent this? We can reduce the size of exhaust area, so this can reduce the convective heat loss through gap. So during the further design, we can look at it. We reduce the size of exhaust area, and then the closing seats that are not used, we remove it. Okay, next is a conductive heat loss. This can be happen during a not well insulated, mostly in a metal stove. Okay, so if we never insulate the stove, it will increase the cooking time because incomplete combustion there. So longer cooking time means that more fuel consumed. So means more money have to be used. Okay, so we can improve by using massive walls to absorb more heat. And then next is a radiative heat loss. This can also happen during the exhaust gap. Okay, so we can reduce the gap and make sure the pot fit on the pot seat correctly. Okay, next is a air supply. This is a major study for mine. During the design, I also improve in the air supply by adding some new features. Okay, so wood, which has a higher heat combustion, it will probably render the heat under the condition of insufficient supply or undersupply of air. Mostly is oxygen, okay? Or even the oxygen is oversupplied, a certain amount of heat will be used in raising the temperature of the excess air. So this never give a good combustion, never give a complete combustion. So the fire is yellowish. Okay, let's look at this table. The minimum requirement of cooking temperature is about 250 degrees Fahrenheit. Okay, so looking at it, normally we have to use stir fry or even a pan fry. So the required heat is quite high. Okay, so this related to our further study later. Okay, next. Okay, so coming to methodology, this is my first design of my cooking stove. This one is the cooking stove labeled in the created in SolidWorks, and then this one is to converted into ANSYS to do the further simulation. Okay, as you guys can see, this is the pot stand, and this is the pot hanger, and then this is the grater. Okay, first stage of the simulation, uh, I do it in a 2D way. So as you guys can see, it's not a very sufficient way because the highest heat we can found here is about 550 degree Kelvin. Okay, and then we can only see at the top of the cooking stove. It's not very sufficient. So after discussing and researching with my supervisor, we improve it by using 3D and better design. Okay, this is the 3D way, and then this is the better design, which I insulated the combustion chamber by using a concrete layer, and then all the heat is trapped inside. And then this cooking stove, this version, I can achieve 5,000 degree Kelvin uh, temperature in the simulation. This is the highest we can go. Okay, so this is sufficient enough to do any kind of cooking. Okay, and then if we close the grater, lesser the airflow, and then the combustion will go down a little bit by about 3,000 Kelvin. Okay, next. So as you guys can see, this combustion chamber is very sufficient. Why? In this simulation of oxygen in the combustion chamber, you guys can see the oxygen is actually close to zero. Means that all the oxygen is used up for the burning. Okay. After that, let's look at the simulation of carbon dioxide emission. This is very important as our project is to minimize the carbon dioxide emission because carbon dioxide can cause a health risk. Okay, in this design, the carbon dioxide still uh the carbon dioxide emission still in a not very healthy level, about 1,067. Okay, so how to reduce it? I studied and then I improve it by adding these two exhaust chimney exhaust. Okay, how to I gonna talk about it later. Okay, as you guys can see, this is the improved cook stove. The exhaust is added. Okay, same I created in the SolidWorks, and then this is in the ANSYS version. Okay, same as just now. This one also having a complete combustion. Okay, the degree or the temperature also 5,000 Kelvin. Okay, also the oxygen here is even better. All the combustion is finished, and then still have a little bit of oxygen left over there uh, because of the airflow coming up. Okay, in this design, the CO2 the carbon dioxide emission is significantly dropped. Okay, this is about 4.5 to 5.25 fraction only. Okay, why? Because the airflow is completed, and then the suction gonna suck it up. So the carbon dioxide is flow out. So as conclusion, a well-designed and well-constructed fuel stove can deliver dependable performance over an extended period of use with the right care and maintenance. The lifespan of the stove can be increased, and the impacts of thermal expansion and contraction can be reduced with regular upkeep and care. Maintenance involves maintaining the stove's specified temperature and fuel consumption range, as well as routinely cleaning, inspecting, and lubricating the moving parts. It is concluded from the new design of the fuel cooking stove, that new improved design would less in cost, sustainable, or less toxic and efficient in heat. Okay, that's all for my presentation. Maybe I'm gonna talk more about the new design. Okay, so actually the fan is added at the exhaust there to create a suction. So the flow of the air can start from the grater and then suck up and then come out from the exhaust and also from the burning area there. Okay, as you can see, the contaction point between the pot stand and also the pot is minimized. Uh, so I create some better airflow in there. Okay, this is my reference. A lot of studies made here. Okay, that's all for my presentation. Thank you.